So we left off in class by calculating these different average rates of change for the function square root x and for the function x squared. This actually gives you a chance to check your answers. So you should have this work in your notebook somewhere for you to check. So our next step after doing all of these calculations is to rewrite each of these four average rate of change problems as limits. Because you can see we're going from 3.5 to 3.9. We're getting closer to x equals 4, the number we're plugging in. So we could just take a limit as x approaches 4. We could take a limit as x approaches 25, a limit as x approaches, looks like we're getting closer to 3, and a limit as x approaches 5 in each of these cases. Because, you know, that seems to be the goal here, and if we want to get closer, we can just take a limit and let this number become closer and closer and closer to 25. So here are those limits. You can pause and get these copied down. Taking a limit as x approaches 4, a limit as x approaches 25, a limit as x approaches 3, and a limit as x approaches 5. And again, all this means is we're going to replace x with a number that is closer to this limit. We're going to replace x with a number that is closer to 4. Replace x with a number that is closer to 25, etc. Okay, so again, you should have these copied down. So what exactly do these represent? Well, without the limit, what are we doing? We're just calculating an average rate of change, right? So with this limit, we're still calculating an average rate of change, but we're letting one of our points become really close to x equals 4. So really, as being, like you can think of this as being y2, and this as being y1, and this as being x2, and this is x1. Right? So this is just, again, a change in rise over a change in run. The only difference is one of our points is going to be a variable, and we're going to let that variable become really close to the other point, right? So what we essentially have here is we have 2 points that are becoming really close together, infinitely close together as x approaches this limit. Okay, so we have a point at we should say, so we have x comma square root x and another point at, in this case, 5 comma 25. Or, sorry, reverse that. Undo. 25 comma 5, right? So then we could call this x2 and y2. We could call this x1 and y1. And what's happening is x1, y1 is getting really close to x2, y2. So you're going to look at this picture now. This is the function square root x. We have a point at, we can say this is x equals 1 and x equals 4. So I want to see what you notice as we go from picture 1 to 2 to 3 to 4. All right, there's some questions on your Google Doc for your group. You can stop this and respond. What do you notice happening as we move from graph 1 to graph 2 to graph 3 to graph 4? You should pause this video now and respond to that question. And then, or maybe you can see if your group has already responded, see if you have something to add, and then you can unpause and then continue. So as the two x values become closer together, the space between the straight line and the square root x graph disappears. We'll go back for just a second. See how there's this space here? And then as that x equals 1 is getting closer to x equals 4 now, that space is still there, but it's smaller. Now we can like maybe barely see it, and now we can't see it at all. So that space is disappearing, meaning that this straight line, it seems to be, at least in this region, seems to be almost the exact same as the square root x line. And if we make them extremely close and we zoom in, we can see that they almost look like they're the exact same line. So the space between them disappears, and then it seems like the green line, at least in this region, is exactly the same as the square root x line. Okay? But square root x is a curve. Square root x is not a straight line, so this introduces an important topic. Local linearity. This is also something you're responding about in your Google Doc. When you zoom in on any curve enough, it looks like a straight line. So here we have a nice, this red, it's a nice curve, but if we zoom in close enough, every point of this curve is going to look like a straight line. So thus we can draw what we call a tangent line, another important vocab word, to any curve. And it's a line that intersects the curve at exactly one point. So this green line is not exactly a tangent line because it still goes through 2 points. It's like x equals 3.9 and x equals 4. right? But those 2 points are so close together that it's almost like they're the same point. So this is almost a tangent line, but a tangent line only goes through one singular point on the curve. And what that's going to do for us is it's going to give us the slope of the curve at that point that it's tangent to, because it's going to go through at that singular point, and if we zoom in on that singular point, that curve would look like a line, and lines have slope. So our next step is to try to represent this picture using a limit. So what do we have? It seems like x equals 4 is staying the same. We've already said this is a square root x function. So square root 4 over 4, right? It's a point at 4 comma 2, right? Another way of saying square root 4 is just 2. Okay, and then what we have is we have this other point that seems to be getting closer. So we'll just call that x. Okay, and square root x, and we're going to take a limit as x approaches 4, because that's what's happening, right? It's x equals 1, and then it's x equals 1.5, and then it's x equals 2.9, it looks like, and then it's x equals 3.9. So what's happening is we're letting x become closer to 4 so that these 2 points become closer together. So the instantaneous, and I'm just going to tell you that the instantaneous slope ends up being 1/4, right? So the instantaneous slope, or the slope of the tangent line of the function square root x at x equals 4. So we have a tangent line that's going through the curve only at one place, at the point that happens at x equals 4. That slope is 1/4. And that means that the function is increasing, but not by much. 1/4 isn't a very steep slope, right? It's a flatter slope. So what this tells me about my function square root x is that my function is increasing, but not that much. And we know that about square root x, because what happens to square root x over time is it starts to get flatter and less steep. So at x equals 4, we're saying that slope is exactly 0.25 or 1/4. Okay? So this is an instantaneous slope formula, but before we actually get into that formula, what exactly is happening here? I should change this from discussion. You're just going to think about this, and there's going to be a response related to this in your Google Doc. So if I let x equal c, we get 0 over 0, and this is something we reviewed in that last unit. What is this? Well, this is actually a hole. And what we really have here is, again, we have this is y2, and this is y1, and this is x2, and this is x1. But if we let x equal c, what that's going to give us is it's going to give us basically like this is y2 is equal to y1, and x2 is equal to x1. So when we subtract them, we get 0 over 0, which causes a hole. So and the reason we're doing this is because a tangent line only goes through one point. We only want it to go through c comma f of c. But this is our formula for calculating slope. It requires 2 points. And if we make those 2 points the same point, it's going to give us 0 over 0, which is an undefined output. So we can't do this, right? We can't calculate 0 over 0, so we have to take a limit. We just have to let this first point become really close to the second point without actually letting them be equal, because that's not going to be a calculation we can do. Okay, so going back to this example, we have, this is our instantaneous slope formula. This is how we always will calculate instantaneous slope. Okay, so from our example, this is the f of x, this is the function. Okay, this is the function with the x value plugged in this case x equals 4. What's square root 4? It's 2. And then this is our x, right, and this is our c, right, which is the x value we're approaching. So this is the average rate of change between x comma root x and 4 comma 2, but we're going to let x comma root x become really close to 4 comma 2. So again, this is something you can just pause and copy down. You can think of this as being y2, this is y1, this is x2, this is x1, and then we're just letting the two x values become really close together, which is going to cause the 2 points to become really close together. So again, pause and copy this down. Another way of thinking about this is that this is our change in y, which we can use this little delta sign and say delta y, and this is our change in x, our delta x. They're both becoming really small, and what our limit allows us to do is it allows us to divide them and see what our instantaneous slope is. So the two x values become really close together, delta y becomes small, delta x becomes small. This limit allows us to divide them and figure out the instantaneous slope. So this last group of slides just wants to drive home the point of local linearity. So here I have a bunch of straight lines, right? Let's make some more straight lines. Okay, here's a bunch of straight lines. Let me add some more, and I think I'm going to add even more. Okay, if I take this series of straight lines, there's probably like 40 straight lines in here or something like that. Well, they start to trace out the path of a parabola, right? So a parabola is a curve we're all familiar with, but now we're thinking about this in terms of calculus, and what a parabola is formed by is actually just an infinite number of straight lines that will end up, they're little tiny segments of straight lines that when stringed together are going to form this nice curve. Okay, so there's going to be a part 2 of this where we actually start calculating instantaneous slopes.